Okay, well, thank you very much, folks, for joining the Deep Space Exploration Society tonight. And we're very fortunate to have Whit Reeve, who is an expert on magnetism, one of the four major forces in the universe, and also the magnetometer that we've got. And Whit's going to give us three presentations to cover the topic really well. And this will be the first of the three presentations, and we'll be posting these on the DSES YouTube page. So, Whit, with that, if you can start off and give a couple of people a little bit of background on yourself, and then carry on. You may want to turn on your microphone. Can you hear me, Whit? Turn on your mic.
Sorry about that.
That's better.
I live in Alaska. I was born here in Anchorage, and I ran my own engineering business from about 1975 to 2009 when I retired. So that's about 15 years ago, 16 years ago. And I fell into the HARP project up here in Alaska, the High Frequency Active Auroral Research Program. And then I also started doing radio astronomy and uh, geomagnetism. Were kind of two major things that I did after retirement, and they actually turned into be more of a full-time job than anything else. And so with the magnetometer now, I have this three-part presentation that I'll do, and it reflects kind of the sum total of my knowledge of magnetism and geomagnetism and the instrumentation that you can use to measure that. And so I've had the SAM-3 operating here in Anchorage since 2000, I believe 2009. It actually started out to be a single axis unit, and then we modified it, and now it's a three-axis SAM-3. That's been in service continuously since about 2009 or so, 2009 or 2010. And it's never missed a beat. The only problems I've ever had with it were with the Windows PC that runs the software. And of course, that's not surprising to anybody. So it really works well. And what I'm going to do, in fact, let me share my screen. Okay, you should be seeing full screen now.
Yep.
Okay, perfect. This is, like I mentioned, this is a three-part series, and the first part is an introduction to magnetism and geomagnetism. In part two, I'm going to show you a series of measurements that I've made since the very beginning. So some of these measurements date back to 2010, gone through a complete solar cycle and into a second solar cycle with this system. And then in part three, we'll go into the details of the SAM-3 itself. So depending on your preference, I could switch part two and three and do this the magnetometer part in part two rather than part three as shown. But I'll wait till after this presentation is done. If you give me some feedback on that, I'll be glad to change the order. So what I'm going to talk about today is kind of a laundry list of things, the basic characteristics of magnetic fields. We'll talk some about the magnetic environment, timescales that we use to measure different magnetic type events. And of course, space weather is one of the big reasons to be measuring Earth's magnetic field because it's really affected by solar effects. And then as well as radio propagation, the magnetic field has direct effect on that, along with the sun. And then I have a list of resources and web links that you guys can download additional information if you're interested. So the first thing is that the Earth's magnetic field has been known about for a very long time, maybe 1,000 years or more, in terms of compass navigation. But the first real scientific study of it was by William Gilbert, and this was way back in 1600. And if my Italian is correct, he wrote a book called Magneti, and it's been translated to English, and it's actually a pretty interesting book to read. It's not a thousands of pages or anything like that, but the English translation is pretty easy to read. Now, our understanding of the origin of Earth's magnetic field is still under debate, and it has been for since day one. And the arguments rage through today. Now, the magnetism, as you probably already know, results from the motions of electric charges, and this can be electrons in their orbits around a nucleus, the spins of an atom or the electron produce magnetic fields through their motion, and a magnetic dipole has a north and a south pole by convention, and it is not known if there is such a thing as a magnetic unipole. At least nobody has found one yet. All the theory that has been written about it, it looks like it's a dipole and there's no other way about it. Now, a bar magnet is a magnetic dipole, and you probably, back in your school days, put a magnet underneath a piece of paper and then sprinkled iron filings on that paper. And I still remember doing this maybe in third grade. And I was really fascinated by the fact that these iron filings would line up, and I couldn't see what was lining them up. And that's the magnetic field. It's a force field. Now, in the Earth, if you go along the surface of the Earth and measure the amplitude and direction of the magnetic field at any point, and then plot it out, it looks very, very much like there's a dipole magnet inside of the Earth. And it turns out, though, that this dipole, this kind of a concept of a dipole, is tilted about 11.5 degrees from the rotation axis, and it's also offset by about 550 kilometers from the center of Earth. So it's not a perfect dipole by any means, but the measurements show that you can describe Earth's magnetic field very well by just calling it a dipole and then making your calculations from there. Now, this image shows the geographic pole here, and so this would be the spin, where the spin axis comes through the Earth at this point, and the magnetic North Pole, then, and this is for the northern hemisphere, is over here somewhere around Greenland, maybe even north or so of Greenland. It wanders around, and if you take measurements of that wandering, that the average position of the magnetic North Pole then is centered by the geographic or spin axis of the Earth. So it wanders around and shifts. Even as I'm speaking, it's shifting. And so it's a really a big problem when you're trying to use compass navigation over long periods of time, because the position that your compass is pointing isn't necessarily, say, to the north that's marked on a map. Now, inside of Earth, it's thought that there's really two layers down really deep. One is a solid inner core, and it's solid because of the high pressure from gravity. And there's claims that it is pure iron, and I'll address that here in just a second. There's also a liquid outer core, and it's the movement between these two cores that generates the magnetic field inside of the Earth. And it's not known for sure that this is the case, but measurements strongly indicate that it is. And of course, we have no way of making a measurement at the site, so we really don't know for sure. But the exact mechanism, even though it may elude us, there's plenty of theory that's been put forth that says, okay, if there's a certain kind of convection in this liquid outer core, and it's moving around this pure iron solid inner core, then a magnetic field's going to be generated, and it's called a dynamo. And that's really an old, kind of an obsolete term, but it's still used to describe magnetic fields in not only Earth, but in the planets and that have them, that has a magnetic field, and in the stars and the sun and so on. Now, when we read science papers about Earth's magnetic field, we have to temper the claims, I guess you would call it. According to Francis Birch, who was a famous scientist, and he clarified how we should read these scientific papers. So when a scientist says in this paper that for example, the core of Earth is solid, pure iron, his translation is, well, that's kind of dubious. And when the scientist says it is undoubtedly this way, the translation is perhaps, maybe, and so on. So, and as far as being pure iron, it really is an uncertain mixture of all elements. So, Francis Birch did us a big favor by clarifying this type of thing for us. Now, in terms of Earth's magnetic environment, the internal magnetic field forms this volume, this force field around Earth. And if there was no solar wind, the magnetosphere, or this volume of the magnetic field of Earth, would be shaped just like I showed in one of those early dipole slides. But what happens is the solar wind compresses the day side of the magnetosphere and stretches it out on the night side, or the tail, and this is called the magnetotail. So here's kind of a cross section of what we see. Now the sun would be off to the left, far off to the left, and the Earth's magnetic field is shown by these lines here. And you can see that on the day side, that it's compressed approximately 8 to 10 Earth radii. And it varies with the solar wind, and changes basically at a moment's notice. But on the downwind side, or the night side of Earth, the tail gets stretched out at least 100 or several hundred Earth's radii. And there's even evidence that it's stretched out, that Earth's magnetic field is actually stretched out up to maybe 1,000 Earth radii on the downwind side of the planet. Now I'm going to show you an animation here, and this is of how a dipole field would look without the solar wind. But then when the wind blows against it, it compresses the upwind side and stretches out the downwind side. And we have this bow shock right here that's on the sunward side of Earth that is the point where the solar wind then flows around Earth's magnetic field. The solar wind can't normally penetrate the field because the plasma in the solar wind gets trapped by magnetic fields and can't easily penetrate it. Now, the average wind speed of the solar wind is in the neighborhood of 470 kilometers per second. The background wind speed, so a perfectly quiet sun with no coronal holes, no sunspots, just a plain old sun surface, the wind speed's in the neighborhood of 300 kilometers per second. Now, when you do measurements of Earth's magnetic field, you find out that there is about, of the total that you're measuring, 90% of it is called the main or internal field. But there's also a 10% external field, and these are components that are mostly or almost entirely controlled by the sun. And one way or the other, the sun controls the so-called external field. Here's some examples of the external field. I'm going to have to take a drink here. There's remnant magnetism in Earth's crust. This is magnetism that's more or less permanent, caused by the magnetic field. There's the magnetic fields that are embedded in the solar wind. The magnetic field, the interplanetary magnetic field, is frozen in to the solar wind plasma. You also have magnetic fields generated by current systems that flow around Earth, and there's the equatorial electrojet, which is at low latitudes, plus or minus maybe 10 degrees latitude. And then you have the auroral electrojets, which normally flow about 67 or so degrees latitude. And the auroral electrojet moves up and down with the solar wind and is quite variable. In fact, it gets pushed down and flows overhead of Anchorage quite regularly, especially lately. You also have anomalous fields, and these are generally caused by maybe ore bodies, or they could be where Earth's magma is been pushed up close to the surface. And this map here, this is down in the Aleutian Islands, and the island over here on the right hand is Unalaska. And there's this note here that says that there's a magnetic disturbance of as much as 6 degrees at this Cape Alec, which is right here where my mouse is. And so if you're in a fishing boat and trying to navigate by compass, then you may run into some problems there. But that's called an anomalous field, and they're usually marked on surface maps that you can buy from, for example, the Geological Service. Now, continuing on with the magnetic environment, I've made a list here of magnetic amplitudes, and this is we can call this magnetic induction or magnetic flux density. And the strongest that we know of are at the surface of magnetars. And these are just extremely heavily magnetized neutron stars. And we have 10 to the 15th Tesla. Now, the Tesla is the unit of measure. of the magnetic flux density, and the surface of a neutron star is about 3 orders of magnitude lower than that. Still extremely, really strong. Now, pulsed electromagnets on Earth, 10 Tesla or so. Permanent magnets, the strongest that I was able to find is 1 Tesla. Your refrigerator magnet is about 10 Tesla. I'm sorry, 10 to the minus 2 Tesla, and so on. So moving all the way down to, say, the human brain, then we have 1 picotesla of magnetic field at that point. So these, you can see from this chart that we go from 10 to the minus 12th to 10 to the 15th in terms of orders of magnitude of the magnetic induction. And that's quite a huge range. Now, another part of the study of magnetic fields, especially geomagnetism, or the timescales, cover an extremely wide range as well. Probably the smallest is in the neighborhood of femtoseconds. We don't really, in terms of Earth's magnetic field, we don't mess with that too much. Magnetic field due to sunlight, for example, but it's a short time scale that does exist with magnetic fields. And then at the other end, we have millions or maybe even billions of years of variation in the magnetic field. And in particular, we have magnetic reversals, which I'm going to be talking a little bit more about in a minute. So this plot, or this chart here, shows kind of the range that we're really interested in terms of the study of Earth's magnetic field. We are often we hear about these whistlers, and I have a recording of those here in a minute. Those are electromagnetic waves generated by lightning pulses, and so those are in the neighborhood of maybe a millisecond or so in terms of time scale. And then we move on up to the solar sunspot cycle, and which is about 11 years plus or minus. And the sun's magnetic cycle actually is 20 years, 22 years plus or minus. So in between there, we have what used to be called micropulsations, but now we call those ULF waves, ultra low frequency waves, and they have periods up to maybe 300, maybe 600 seconds. Ring currents, they vary on a 24-hour time scale. The sun itself rotates, and it's on a 27-day plus or minus time scale. Now here's a recording of some whistlers. You probably have heard something like this before. This is from NASA.
1996, hour 0, minute 16, whistlers.
So that was a recording of whistlers, and notice the time scale on this plot that's shown here that's associated with this recording. It's 15 kilohertz maximum frequency. So the whistlers that you heard were in the neighborhood of maybe a few kilohertz, and they sweep from a high to a low frequency due to the dispersion flowing through Earth's ionosphere and atmosphere. Now, as far as the sun rotation goes, it has a 27-day period roughly, and it varies by latitude of the sun. It rotates faster at the equator than it does at the poles, and the rotation rate of the sun was discovered by people watching sunspots, and this animation here shows the sunspots. When a sunspot comes into view over here on the left, it takes about 2 weeks or so, plus or minus, to cross over and then go off of the other limb. And if you have persistent sunspots, you can actually count the number of revolutions that they make. Another aspect is the secular variations, and these are the drift of the magnetic North Pole and the magnetic South Pole, and how it affects a compass with respect to true north or true south. And these variations go over periods of years, but they definitely are something that we're aware of. And for example, when I was learning to fly in 1965, the declination at Anchorage was about 26 degrees. And this is the difference between true north and magnetic north at Anchorage. In 2025 today, it's about 14 degrees. So it's the magnetic North Pole has drifted a lot since then. And I also did a calculation for the DSES dish down there in Colorado. And the declination at that in 1965 was about 12 degrees, and today it's 6.5 or so degrees. And so that the Earth's magnetic field is varying very slowly, as well as relatively quickly. And when it moves relatively quickly, it's called a magnetic jerk. And this is where you have some significant change in the magnetic declination in a period of less than 1 year. And if you look at the scale on this chart here, this is made by the British Geological Organization, and this is the scale on the vertical is about 15 minutes of arc or minutes of change per year. So this is what, a quarter of a degree or so. And you can see though that the trace is slowly moving up, and then it changes direction, and that's called a magnetic jerk. And this plot here covers from about 1900 to 2010. And what's interesting about magnetic jerks is that they may be, you may record them at some geographic location, but if you're, say, 1,000 kilometers away or 500 kilometers away, you may not see that same variation. So these magnetic jerks, they don't really know what's happening or why, but they seem to be kind of regional or local. Now, another aspect of the magnetic field in terms of time is these magnetic reversals. And this is where the North and South poles swap ends. And it turns out that if you wanted to put an average period to this, it's about 100,000 years, at least over the last 25 million years. And the problem is though, that the range of years between reversals is so big that an average doesn't really mean much. And this chart below shows that the black and white indicates a reversal. And you can see that there's quite a few reversals early on here, but then there aren't any for quite a long period of time. And then it speeds up again. So the reversals were discovered through study of paleomagnetism, and I've always wondered about this myself because I always thought that the error bars on these types of measurements would have to be awfully large, and so it's probably lucky that we talk in terms of millions of years and try not to nail down the exact date of a particular reversal. To me, the error bars would just be too big to really home in on that.
Question.
Yeah, is there a question?
Yeah. Um, so are you saying that you believe that the error bars are fairly large?
That's what I believe, yes.
Um, so they got most of this information from the rift zones. Um, do you, and those, by my understanding, are um, fairly consistent in terms of growth, or at least you can detect their velocity as they're growing. So it seems to me like that, it would be actually fairly narrow error bars for this.
It's
Yeah, and
based
I
on
guess
the,
I guess that's something we could debate. I'm definitely not an expert on paleomagnetism, but it just seems intuitive to me that the way this is measured, that it to me it can't seem to be super accurate.
isn't it based on the carbon dating of the rocks that changed polarity?
Yeah, I really don't know the exact way it's measured, but
It's impossible for carbon dating because carbon 14 has a half-life of only about 3,000 years or so, and so you get a few more half-lives of that, and it's non-existent. So you could do maybe uranium isotope dating, but and if there's not carbon, if it's a total mineral, there's no carbon there, so wouldn't be carbon dating.
Yeah, the volcanic um, magma doesn't really have, carbon dating is usually used for biological sources. Since you stop, when you die,
Yeah.
you stop uptaking carbon. So because this isn't biological, I don't think that carbon dating would be used at all in that case. You'd just be looking at the seafloor.
well, there's one thing for sure is that you're going to hear a lot of opinions from me today. So, I'm glad that you disagree with it because um, I'm not an expert on this,
Well,
and
it's the mid Atlantic, the Middle Atlantic Ridge, which has that very constant magma outflow. This is what's being referred to there. Is I believe quite accurate in terms of the flow rate and then the velocity of these layers as they come out, and then as because of the Curie point of the magnetism when it gets below the Curie point, then it freezes in that magnetic orientation. And so that can be determined quite accurately, the magnetic orientation. And then knowing the flow rate out of the mid-Atlantic ridge, you can calculate out the time quite accurately. So I believe that's the point. Now, I don't know how long the Atlantic ridge can go back, what that flow rate is. So if you're going back like this 100 million years or something, I don't know if that's able to be accurate back then, but certainly within the more recent sort of few tens at least millions of years, it'd be quite accurate. But those error bars could be quite significantly large on some of these determinations way back. But the more recent ones, I think, would be quite accurate, at least from my understanding.
Yeah, it gives me something to dig into. Thank you. Um, I'll, I'll I'll withdraw the question at this point.
here's an animation of what happens during a reversal, and this is based on a model. So how good the model is, who knows? But there's probably some credibility to it, and I'll go ahead and play it. The blue is the North Pole, red is the South Pole. So this spans about 100 million years and or so, and you can see that all of a sudden, more or less all of a sudden, that the North Pole is at the bottom and the South Pole is at the top. And so again, this is based on a model and trying to, and the model, what the model tries to do is replicate what the measurements have shown. And apparently this model does a fairly good job of that. And it's interesting to watch. Now, there's also daily variations in the external field, and these are only a few tens of a nanotesla. So these are really quite small, and you can see a plot here that I took with the SAM magnetometer back in 2009, and it shows a daily variation here, and now it's it's arguable whether some of that variation is due to temperature changes at the depth of the fluxgate sensors, or if this is really a local variation. And after operating this magnetometer for, what, 15 years now or so, 16 years, I'm going to say that this is probably due to a daily variation in the magnetic field rather than temperature change. Now, we can't talk about Earth's magnetic field without talking about space weather or vice versa. Some of the major sources of geomagnetic disturbances are the solar flares, coronal mass ejections, which are a huge mass of particles that are ejected from the sun's corona, coronal hole high-speed streams, which is enhanced solar wind. So it's, in other words, it's a faster, higher velocity wind than background. We also have co-rotating interaction regions, and that is where a slow speed solar wind is overtaken by a higher speed solar wind, and it causes an interaction region there and a shock region that is measurable at Earth. And then you have your solar sector boundary crossings, and this is because the region between the sun's northern and southern magnetic fields produces a current sheet in between the two, and this current sheet wobbles over time. Now, the solar wind carries with it part of the sun's magnetic field, and the sun's magnetic field is called the interplanetary magnetic field, or IMF, and it's frozen into the solar wind plasma and moves with it. So if there's this frozen in concept means that if there's a movement in the plasma, the magnetic field lines move with it. Or if there's for some reason, something causes the magnetic field to move, the plasma is going to move with it. So they work together or move together. And one of the things that happens with the IMF, if it has a south pointing component, it'll connect or merge with Earth's north pointing magnetic field. And in this case, when we have this merging or what is called reconnection, the sun's magnetic field is then directly linked with Earth's magnetic field. And this invariably produces storms, magnetic storms and substorms that we can measure with ground magnetometers. Now, any kind of active solar phenomena is going to cause a wild gyration in the magnetic field. This image here shows a coronal hole on the Earth's sun as this dark region here. This actually is a cross-equatorial coronal hole. Normally, the coronal holes are in the lower or the northern and southern hemispheres, but this one actually is large enough where it crossed over the equator of the sun. And what happens with this coronal hole high-speed streams is that you have enhanced solar wind, you have higher speed, lower particle density, and by higher speed, I mean in the neighborhood of maybe 500 to 800 kilometers per second, whereas the background is in the neighborhood of maybe 450 400 kilometers per second. Now, when you have a coronal mass ejection, this is different from a high-speed stream. It's where you have maybe 1 trillion tons of matter blown away from the sun as a huge explosion, and it's called a CME, or coronal mass ejection. This image over here on the right shows one. These loops that you see are particles that are trapped by magnetic field lines from the sun. And one of the kind of interesting things that come from most CMEs is that you have a radio signature associated with them. So if you have a solar radio spectrometer like the Callisto, then you can actually measure the speed of these coronal mass ejections. These are called, the radio signature is called a type 2 slow sweep solar radio emission. And so you can measure that with your Callisto while you're watching the effects of it on your SAM3 magnetometer. Now, coronal mass ejections have quite a variable speed. It depends on what causes them to be launched, and a lot of other factors. You can see that there's a number of coronal mass ejections shown on this chart that are far lower than the background. So the normal wind speed is in the neighborhood of, say, 450 kilometers per second, but we have a significant number of CMEs that flow at a rate of 100, maybe 200 kilometers per second. We also have some that flow really, really fast. And this chart only goes up to about 1900 or so kilometers per second. But just recently, within the last, I think, month or so, there was a CME that was measured at about 2000 kilometers per second. So that's pretty fast, gets to Earth in what, about a day or so. Now I'm going to show some animations here, or movies of a CME. The one on the left is going to go first, and you can see that there's a flare and then this mass of particles. And if you watch that again, you can see that these particles flow in kind of loops, and that's because they're following magnetic field lines of the sun. Now, this one on the right is really interesting. It's been speeded up, of course, and covers a period of about 3 weeks. And I want you to watch the background. The star background is moving left to right. And then we have this guy in a spaceship, and he didn't get the word, and he's going the other way. So let's watch and see what happens. Each one of these puffs that you see is a coronal mass ejection. And all of these are going off to the side of the sun, but then eventually we get some that are blown toward the coronagraph that is actually measuring, making these movies, like right there. And that would have been called a full halo CME, because it seemed to come from all directions from the sun. And we don't know which direction. If it's coming toward the camera in the GOES spacecraft or the SDO spacecraft, or if it's going away. But when we see all those sparkles, we know it's coming toward us. Now, magnetic reconnection is shown in this animation here, and the black lines that you see coming from the left, that's the sun's interplanetary magnetic field. And it's in this animation, the magnetic field has a southward component and is able to connect with the Earth's northward component right there. And these field lines then are blown over Earth, over the top and bottom, and stretched out into the magnetotail. And you can also see that not only do we have this merging or this reconnection on the sunward side, which is on the left, but we see that the magnetic field lines eventually reconnect over here in the magnetotail. So generally, when we have a reconnection event on the sunward side, sometime later in the neighborhood of a few hours, we'll have a reconnection of those magnetic field lines in the magnetotail, as shown here. And when that happens, the magnetic field is being jostled here, and we'll see that we'll see those effects on the ground magnetometer. And another thing that happens when this connection makes right here, solar wind particles can actually enter Earth's magnetic field at that point. And this causes a lot of radio effects, so which are detectable by your Callisto instrument as well. A manifestation of space weather or solar activity is visible aurora, shown on the right. And in fact, I have another animation here on the left I'll show you. And this takes just a second, and then it shows the aurora that's been imaged by some kind of a spacecraft. So the image on the left is from a spacecraft, and the image on the right is from the ground. But you get visible and aurora and radio aurora, and that brings us into radio propagation effects. Now, with the radio and visible aurora are actually separate phenomena, but they have the same origin. They don't always occur at the same time or together, but very often they do. So in other words, if you have visible aurora, then there's a pretty good chance that you have a radio disturbance of some kind, either a radio blackout or radio aurora reflections and things like that. So radio aurora is enhanced ionization of the neutral gases in the atmosphere, and this causes reflections of the radio waves below the plasma critical frequency. And the visible aurora, on the other hand, are light emissions through the excitation of the neutral gases by the particles that have entered Earth's magnetosphere during a reconnection event. Now, the radio aurora, if we have it, it usually is in the neighborhood of 100-kilometer altitude, and visible aurora generally is from maybe 80 or 90-kilometer up to maybe 400-kilometer altitude, whereas the radio aurora and the reflections associated with them are generally in the E region of the Earth's ionosphere. Now here's a comparison of the SAM magnetometer magnetogram over here on the lower left, and chart that was made with Argo software. And the Argo software takes the demodulated signal and displays it in a very, very narrow spectrogram. So this spectrogram covers this particular one from about 990 hertz up to 1020 hertz. So this is the way the receiver is tuned. It would provide, in this particular example, it would have provided the carrier would provide a 995 hertz demodulated signal. And But because of these aurora radio reflections that I was measuring here, you can see that there was a change at where this arrow is shown here on the left on the magnetogram, and the yellow arrow on the right on the Argo plot. Those are at the same time. So we had this event over here, this magnetic event that caused these radio phenomena that we're showing on the Argo plot. Here's another example of aurora radio reflections that I measured here at Anchorage. This plot shows a 2-hour period, and you can see that I've put yellow arrows here at 30-minute intervals. And so here we had enhancement. This was actually a WWV station that I was receiving in this case. We have an enhancement, and then it drops out. We have another enhancement, maybe 15 minutes later or so, a dropout, and so on. So those are auroral radio reflections, and this is a direct radio propagation effect of a magnetic disturbance. Another thing that can happen are ionospheric storms.
Question?
And did I hear a question?
Yeah, on those WWV, is that the shortwave emissions, or is that the is that the low frequency transmission?
Yeah, this is the HF. So this, I believe this chart here and the one before was using the 15 megahertz transmitter at WWV.
Thank you.
Ionospheric storms, disturbances in the ionosphere are generally related to some type of magnetic disturbance. And what happens is that when you do have a magnetic disturbance, sometimes the disturbance can last for days at a time. And what happens, you have additional currents in the ionosphere. You have geomagnetic disturbances that you measure on the ground. You have reduction in daytime critical frequencies at in the F region. So that's a radio effect. And you can have enhanced spread F or even sporadic E propagation, radio blackouts. So ionospheric storms are generally detrimental to radio propagation, but you can measure their effects. At least in Alaska, you can, because we're near the auroral electrojet, and any kind of a current change there definitely going to show up on your magnetometer. Now, you guys are about, I believe, 40 degrees or so north latitude. Does that sound about right? 40 or 45 degrees. You're not going to see the effects of the auroral electrojet unless it gets really pushed down. And it can do that. It can be pushed down by a magnetic disturbance, and so you could see the effects even at your lower latitudes where you guys are. Now this is a animation showing a quiet ionosphere on the left versus an ionospheric storm. And notice that the storm is kind of a global event that's being shown here. And so you can see that there's ionospheric activity over here on the left, but it's greatly enhanced over here on the right during storm conditions. And this is a measure, by the way, these plots here are measures of the total electron content. So that's a column of electrons from surface to out into the upper end of the ionosphere. Another radio propagation effect, and this is at up near the poles, either north or south pole, you can have polar cap absorption. This is called PCA, and it's enhanced ionization at high latitudes, generally within about 20 degrees of the magnetic poles. And these always lead to radio blackouts, because what happens is you have extremely heavy absorption in the D region, and any kind of radio wave that's trying to propagate up through that D region is going to be attenuated to nothing before it can get up to refract and go on its way. And these events can last from hours up to days or even a week, depending on the latitude. You also have ionospheric patches and blobs. Again, these are related to magnetic activity, and this is where you have greatly increased or decreased ionization, usually at higher latitudes. But now during a really strong geomagnetic storm, these types of things can be pushed down to lower latitudes. So you may be able to actually detect them with your magnetometer there in Colorado. So that pretty much brings us to the end of this presentation. I have a list of resources and web links here. Of course, you can't click on them where you are, but if you want any of these, I can put them into chat or send them in an email to you if you want any specific information. I have the SAM magnetometer showing real-time data for Anchorage. I also have a SAM up at the HARP facility, which is about 300 kilometers from here and north and east of here. And that's online as well. You can find the documentation for the SAM. If you want to order, there's information online for that. The construction and software setup manuals are online. You can download them. They come with the kit on a USB or a CD, depending on when you bought it. There's also a geomagnetism tutorial that I wrote a number of years ago that I've been told is really good. So you might want to download that and take a look at that if you're interested in learning a little bit more about this. And then, of course, you have the Space Weather Underground, which uses the SAM-3. And both here in Alaska and back in New Hampshire, they've built a substantial network of SAM-3 magnetometers. And even NASA has gotten involved in this and has sponsored a number of people or a number of universities in Michigan and elsewhere where they bought the SAM and are building their own networks for space weather studies. So that pretty much brings me to the end. I'll be glad to take any questions if you have any. I probably fed this to you in terms of a fire hose, and I apologize for that, but we'll pick it up the next time for sure. And hopefully you'll enjoy the next episode in a month.
Could you supply those links to Paul in a readable form? Paul, could you distribute those maybe using Group IO or something like that? So I have some clickable links.
Yeah, what I'll do is I'll just send this page to Paul, and the links should be clickable in the document that I send him. So
Okay, great.
yeah, that I can do that when we're done here.
Great.
I did a screen save, and I can send that to Paul.
You can,
Yeah, that wouldn't have a clickable link though.
No, you'll have to copy it and take it to a.
yeah. He's
Yeah,
gonna
some of the links are pretty long, but I'll send them out and make it. Hopefully, they'll be clickable for you, and you can go right to the sites.
I had a question, this Bill. Is there any relationship between the sun cycle and the geographical uh, uh, volcanic and Earth, I don't know, seismic activity that we're seeing recently?
Um, yeah, that's a good question. I have seen some papers that have argued that yes, that is the case, and other people have tried to debunk that. And so, from my perspective, I really don't know. I think there is some evidence that there is some kind of a correlation between seismic activity, VLF radio propagation, solar wind, and all that. But yeah, that's a debatable question, I think.
Okay. The other comment I would say, you say you've got two more parts of this series that you'll share with us down the road. Something we'd all be kind of interested in because there's a lot of mystery surrounding it, and that's the harp, what harp's all about.
Oh, yeah. I do have a presentation on HARP, and I could do that if that's what you'd like to see. Um, Yeah, it's really not a mystery. At least now it isn't. Maybe when the Air Force operated the site, um, they weren't very good about telling anybody what was going on, and you can't blame them for that. It's military operation, right? But and now it's being operated by the University of Alaska Geophysical Institute. It has been owned by them since 2015. And so I got involved with them in 2016, and I spent actually have spent quite a bit of time up there, and I'd be glad to do a presentation on it if you guys are interested.
Yeah, maybe down the road when we finish this group.
Yeah, that'd be great. I'd be glad to do it.
And I think it would be somewhat useful to have the how the magnetometer works precede the data from the experiment.
Yeah, let me go to the very front. Whoops, I went the wrong way. I'll get there eventually. It's not letting me go to the first page, but I'll scroll all the way up to it. Okay, there we go. So what you're saying is you'd like to swap part 2 and 3.
Well, that's just me because I think it would help to understand the measurement better.
Yeah, yeah, that's a good point. And so yeah, let's plan on doing that. And so in July we'll discuss the SAM-3 itself, and then in August we'll do some of the measurements that I've made over the last 15, 16 years with that device.
Yeah, that'd be cool. Okay.
Okay, great.
I had
And Bill,
a question.
go ahead.
Oh, well, okay. I was just wondering if you had any information or any comments you might have regarding the South Atlantic magnetic anomaly, and if you had anything to say about that.
Uh, I haven't spent a lot of time on that. I'm aware of it, and I do know that people that are in that part of the world are really interested in making magnetic measurements of it and the changes and how it has changed. But I don't really have a lot of knowledge of it myself. Um, if you're interested, I could probably dig up some. These would be science papers written by uh, uh, people at observatories that are in that part of the world. And maybe that would give you some background information that you could use to pursue it.
Okay. No, I was just curious if you had any maybe updated information. I was just
No, I
eh,
don't have anything other than these few papers that I've downloaded over time.
okay. I was just curious. I mean, I've been aware of that for phenomena for quite a number of years, and just wondering if anything more recently had been done as to its potential costs. I know that there's some claims that it might be associated with perhaps initiating some of those geomagnetic reversals that you described, and that it might be somehow associated with almost like a nucleation point for that magnetic flip. But other than that, I was just curious if there was any more information regarding that. But anyway, just my curiosity, not nothing that you need to
Well,
delve into.
there are so many mysteries associated with Earth's magnetic field that you almost have to. I mean, if you want to really study something, you almost have to pick a subject and then concentrate on that for the rest of your life, because there are just so many of them that people have tried to explain, and for every person that says they have the answer, there's 10 that says they're full of it, and and the other way around too. So
Well, it's called the scientific process. That's how it
yeah,
works.
that's what it's called, all right.
You mentioned several groups that have a number of these SAM units that are gathering information. Is there any worldwide aggregation of data being done?
No, there isn't, and this is something that we've discussed over the years. The problem, it would be a voluntary effort, right? It's well known that voluntary efforts only last the life of the people that are really interested in doing it. And so we've never been able to come up with a way to archive the data over the long term. And of course, the other problem is the quality of the data. We don't, with a lot of these installations, we have no knowledge of how well they're controlled and things like that. So it's a it's a big problem. It's too bad. I would really like to see the worldwide data archived, even through SuperMag or something like that. But it would have to take somebody that say, okay, I'm going to do this, and if I can get funded to do it, great. If not, I'm going to do it anyway. But without that, it's just not going to happen.
Okay, a secondary question is, would you, so I was voluntold to kind of set up our experiment, and I would like to do it in a very um, scientifically rigorous manner. Do you mind if I contact you with, some of our proposed installation configuration to see
Oh,
if we,
absolutely. Yeah,
okay,
I'd be glad to help you with that any way I can.
very good. Thank you.
Well, it wouldn't be ground data, but wouldn't there be a significant sort of mapping of the geomagnetic field from satellite, even low orbit satellites? I would imagine that maybe NASA or somebody would have records of measurements like that. Wouldn't you think?
Well, the repository for magnetic data um, from virtually everywhere is SuperMag. And what they've done really a great job, because they've taken data that and they've curated it and purified it to eliminate a lot of the problems with basically random data from some observatory that existed 50 years ago. And so, yeah, there is a place where that stuff or professional data is located, and it's called SuperMag.
Okay, I think we got most of the questions answered tonight, and thank you so much for your time, Whit, and appreciate you coming on to onto our Zoom tonight. And we look forward to the next show
Yeah, great.
that you're going to do, and that'll be the magnetometer itself. And I'm kind of excited about getting this in there. We're doing a lot of digging around our property lately, and we're going to be doing more of it. We've got some fiber coming in this week, so they're going to be doing a lot of trenching, and we just need to figure out where we're going to put the magnetometer and hopefully find a backhoe somewhere.
Yeah, put it on the north side of a building if you can, so that the sun doesn't, bear down on it directly. And if you have any kind of a shrubbery that you could be planting, plant some shrubs around it too, and that'll help keep temperature variations down.
We have lots of weeds.
Yeah, lots of weeds.
But our property is pretty much, let's put it this way, it's unobstructed. There's not too many buildings around. The closest town is about 5 miles away. And
Yeah,
The closest tree is 5 miles away, Paul.
that's true. Yeah, that's right. That's right. So we don't really have too much. Like I said, we don't plant much out there because it's a desert
yeah.
down there.
And is it, I know over Stan Nelson in Roswell, he calls the desert around there desert pavement because it's like asphalt. Is it really, really stiff like that
It's
at your site?
it's kind of like being on the moon with all that dust.
Oh, it's really dusty. It doesn't
Yeah,
have a really hard surface.
Now, Will, it's like flour when it's dry and the wind blows it all over, and when it gets wet, it's like dough and it sticks to your feet and builds up.
Oh, yeah.
And and it goes from one state to the other and everything in between.
the fluid environment. So
Yeah.
in any event, I'm sure I'm sure we'll figure a way to bury it far enough down so
Any-
we
Any problems with prairie dogs digging